Hello APC Mechanics students, today we'll solve the past paper FRQ 2019 Set 2, exercise number 3. Then always remember that the figure appears above the text. The rotation inertia of a rolling object may be written in terms of its mass and radius as I given by BMR square, where B is a numerical value based on the distribution of mass while within the rolling object. Students wish to conduct an experiment to determine the value of B for a partially hollowed sphere. The students used a loop track of radius r much greater than r, as shown in the figure above. The sphere is released from rest at height h above the floor and rolls around the loop. Now in part A, we need to derive an expression for the minimum speed of the sphere's center of mass that will allow the sphere to just pass point A without losing contact with the track. Express your answer in terms of BMR and fundamental constants as appropriate. Now we know that the force responsible for dictating the contact to the surface is the normal push. So here they're talking about the expression for the minimum speed in order just to pass the point A without losing contact. So we need basically to apply Newton's second law at the point A and set the normal push to be 0, and that would give us the expression for the minimum speed. Then because we're applying a big law, we need to say apply Newton's second law, and that would be given by F naught is equal to MA. Now here, what are the different forces that are acting at the point A? We have the pull of gravity down, the normal push is down. Then that would be the pull of gravity plus the normal push is equal to MA. But remember, this is a vector relation, can be projected along different directions, and the normal push is pointing, so let me say it again. So at the point A, that's the rolling object, we have the pull of gravity down, we have the normal push down. Why the normal push is down? Because it's always perpendicular to the surface, and notice that the sphere is in contact with the surface from the bottom, so the normal push would be perpendicular downward. Then in this case we need to project along the center. Then we can say projection along the centripetal direction. And remember that whenever we're projecting along the centripetal direction, what is the positive direction in this case? It is not up or down, it's always toward the center, and it happens in this case that the positive direction is along the pull of gravity and the normal push. So in this case, that would be the pull of gravity plus Fn is equal to MAC. Now the pull of gravity is given by mg plus Fn, and because we have projected acceleration along the centripetal direction, it can be written as v square divided by the radius of what we have, 2r, small r, big R, but that would be the radius of the circle that we have. And now we need to set the condition given by Fn is equal to 0, loses contact. And in this case, that would be mg is equal to mv squared divided by r. Now m with m would cancel, and the minimum speed would be given by the square root of r multiplied by g. This is it for part A. Now in part B, they're telling us, suppose the sphere is released from rest, which means the initial speed is 0 at some point P. That's the point P. And rolls without slipping. Derive an equation for the minimum release height h that will allow the sphere to pass the point 8 without losing contact with the track. Express your answer in terms of BMR and fundamental constants as appropriate. Let me take a step backward and check that indeed our answer is expressed in terms of R and fundamental constant. Don't expect that your answer always should be expressed in terms of all the physical quantities that they have suggested. Now here we have rolling without slipping. This is important because we will have two types of energies. rotational and translational. And because we're interested in relating the height to the point A, which is related to the point of losing contact, then we need to apply the conservation of energy. And here, the conservation of energy, before we apply it, we need to set our PE level. So usually we take it to be the final position of the center of mass. So if you think about it, it would be here, but here it would be challenging to include this height. So it's easier for us to take the PE level to be at the center, to be at the bottom level. But the thing is that now we have the point B and the point A. At the point B, because it's released from rest, the initial kinetic energy would be 0. We have a gravitational potential energy. At the point A, what types of energy we have at the point A? Don't think that because we're about to lose contact, then the kinetic energy is 0. No, because the biggest proof on that, we have determined the speed, which is given by radical r multiplied by g. So we have at the point A kinetic energy as well as gravitational potential energy, because that would be our PE level, and we have a height equal to the double of r. So let's first state that take the PE level to be the lowest, horizontal level, and now because this is a big law, we need to say apply conservation of energy. Which means energy initial is equal to energy final, and energy is about being kinetic and the gravitational potential energy, and that would be kinetic energy and the gravitational potential energy. Now the initial kinetic energy is given by 0, and here we cannot say that the final gravitational potential energy is being 0, and we have justified that. Now the mass of the object that we're working with is m, so that would be mg, and the initial height is given by capital H. Now we have said that the motion is about being translation and rotation because we have rolling without slipping. For this reason, at the point A, we need to say that we have both half I omega square plus half mv square plus the gravitational potential energy, which is related to the double of r. Then mg multiplied by the double of r, and we're interested in determining this height. Now what makes us sure that this height is the minimum height? If we replace the speed by the minimum speed given by the square root of rg. Now the rotational inertia is given by bmr square, so that would be mgh is equal to half bmr square omega square plus half m. Now the speed is given by the radical rg to the power of 2 plus mg, the double of r. Now m with m would cancel, then gh is equal to half br square omega square plus half rg, because the power of 2 cancels with the radical, plus 2rg. Now still we need to relate omega to the speed, because we have rolling without slipping, so we can say that omega is equal to v over which radius. Here we have two radii, this one and this one, but because here the rolling is happening around itself, so we use small r, then that would be v divided by r. So let me complete my expression here. That would be gh, which is equal to half b r square v square divided by r square plus now 2 plus half, that would be 5 over 2 rg. Now this cancels with this. Again, v should be replaced by radical rg, so that would be gh is equal to half. Now radical rg with power to cancel, so that would be rg plus 5 over 2 rg. Now we don't forget the b, which is here. then G with G cancels, so H is given by half RB plus 5 over 2R. Then finally H can be written as, we can factor out R over 2, so that would be R over 2 into 5 plus B, or B plus 5. And now we can continue. The students perform an experiment by determining the minimum release height H for various other objects of radius R and known values of B. They collect the following data. Now these are the data for B, and these are the data for H. So each time they measure B, so for different values of B, we have different values for H. Now on the grid below, plot the release H as function of B. Usually in the exercises they don't specify for us what are the quantities to be measured, to be plotted on the y-axis and the x-axis, but here, since they're mentioning that H as function of B, which means that this should be labeled by H and this should be labeled by B. Now how do we know the units? We need to refer to the previous table, and so B has no unit, H is given in meters, so that would be in meters. Clearly scale and label all axes, including units if appropriate. Draw a straight line that best represents the data. So we need now to divide our grid based on the following. Now if you notice that H doesn't start from a zero value, even if we have started H from a zero value, the splitting of the numbers would be very difficult, because we need to jump from 0 up to 1, and the difference between all of these numbers is very small. So a good way to divide the y-axis, the h-axis, is to consider it by step of, so we can start by 1.0 and we divide it by step of 0.05, because we can reach 20 by 4 values. So let me say that would be 1.00, 1.05, 1.10, 1.15, and our final value would be given by 1.20. And here let me state something very important, that it's not always necessary to start from the origin. Alright, you can directly start from a certain value up to our convenience. Now what about the b-axis, the x-axis? Since we need to reach 1 starting from 0.4, so it's reasonable, and if we have 1, 2, 3, 4, we can divide it by a step of 0.25. So that would be 0.25, 0.50, 0.75, and that would be 1.00. So I think this splitting would be enough for us to include all the values. Now the first point is given by 0.40, 1.08, then 0.40. So if you notice that here we're moving by a step of 0.05, so 1.05, 1.10, 1.15, 1.20, sorry, 0, 0.05, 0.10, 15, 20, 25. So 30, 35, 40, so 0.40 would be somewhere here, and we need 1.08, so the first point would be somewhere here. Now our second point would be 0.67 with 1.13. Then 0.67, let me double check. 0.67, let me write them down. 0.67 and 1.13. Then 0.67, this is 55, 60, 65, 70, so it's somewhere here, and we should go up to 1.13, which is almost here. So I think that's fair enough. Now the other point would be 0.50 by 1.10, that's easy. 0.50 by 1.10 here. So notice that the values that are given in the table, they are not in order, and the final point would be 1 versus 1.20. Then that would be 1 with 1.20, which is the final point. Now we need to draw our best fit line and make sure that it passes through almost all of the points. Now in this case that's easy. So this is a best fit line for all the points, and you will notice that only this point is out of the data. Okay, so this is it for part C. We have stated clearly our labels, we have did the scale, and we have plotted the data, and we have done the best fit line. Now in part D, the students repeat the experiment with partially hollowed sphere and determine the minimum release height to be 1.16 meters. Using the straight line from part C, determine the value of B for the partially hollowed sphere. Now, what is useful about this best fit line? So the first thing is that we can determine the slope. This is something that we're used to. But another important thing is that if we know the value of H, we can determine the value of B, and we know the value of B, we can determine the value of H. So one can think type, what's the difference between this graph and this table? Now this table has limited values for B and H. So it only gives us 4 values, 4 correlated values. However, when we draw the best fit line, this would give us many values ranging from 0 up to 1.00 and 1.00 to 1.20. And indeed, they're telling us to determine the value of B if H is 1.16. I repeat that 1.16 in this case is not accessible from the table. We are only limited to these values. But because we have done the best fit line, now it's accessible. So 1.16 if you refer to the curve. So this is 1.16. So let me label it here. And if you go like that, now it's better not to represent it on the graph itself. Let's keep it like this. So 1.16 would be 0.80. Now here we need to explain that we have used the graph. So it's good that we write it graphically. To indicate that we have used the graph for H is equal to 1.16 meters. We have that B is equal to 0.80, which means then B equals to 0.80. Now they're telling us to calculate the radius of the hoop. Now again, the radius of the loop, which is this loop. Now again, we should think about the curve. Now notice that the radius of the loop appears here in the following linear relation, which is given by H. So let me write it here. H is R over 2, B plus 5. And this can be written as H is equal to R over 2, B plus 5, R over 2. Now if you're considering H as function of B, this is a straight line. And the slope in this case would be R over 2. So basically, if we determine the slope, we have determined R over 2, then we can deduce R. So let me say, okay, here's something very important to mention that I was thinking about. Notice that this is the line, this is an equation of the line that's not passing through the origin, but according to this drawing, it's passing through the origin. But remember, that's not the origin, it has been shifted. So let's determine the slope. And in order to determine the slope, we need to choose 2 points. Remember that these points should not be the points that included in the table. They should belong to the new best fit line. So I will choose this point, which is very perfect, and this point, which is very perfect, and make sure that as long as the points are more separated from each other, the better our results would be. The first point has a coordinate of 0.25 with no units, with 1.05 meters. So the slope in this case would be given by, and the second point is given by 0.75 and 1.15. Then 1.15 meters minus 1.05, that would be in meters, divided by 0.75 minus 0.25. Now plugging that fraction on the calculator, we would have that the slope is 0.20 meters. Now we need to do the linearization. We know that the equation is given by H is r over 2 into b plus 5, which means that would be r over 2 b plus 5 over 2r. Then which means that if you compare, that's the slope because h as function of b, then the slope is given by r over 2, then r is given by the double of the slope, then r would be given by 2 times 0.20, then r is given by 0.40, and the SI unit of r is given in meters. Now finally the last part of this exercise. In part B, the radius r of the rolling sphere was assumed to be much smaller than the radius r of the loop. If the radius r of the rolling sphere was not negligible, would the value of the minimum released height h be greater, less, or the same? Now here we have done an assumption that r is much bigger than r, which means that this is a particle, and when it enters into the loop, the radius that it will perform is the radius of the loop itself. Now they're telling us, assuming that the small radius r is now not negligible anymore, which means that this small particle now has dimension like this, and it's rolling inside the loop. Now the thing is that what will happen is that would be the trace for the center of mass. So you can notice that in comparison with this small size, you will notice that if this sphere has dimensions, then the radius of the circular track that it will occupy is less than r, which means that r has been decreased. So if the particle has significant dimensions, which means its radius is not negligible, then it will perform circular motion inside the loop, but with a radius smaller than r. So we can say that r decreases. But what's the relation between r and the height? Here, h from this relation obtained in part B is directly proportional to the radius, not exactly of the loop, but the radius along which the particle moves, which means if r decreases, then h decreases. So let me here say the choice would be less, because since the radius of the object is not negligible anymore, then the center of mass of the object travels in a radius less than r. And from the equation from part B, h is equal to r over 2 into b plus 5. As r decreases, h decreases. Then that's it for me in this video, guys. See you soon in a new one.